Last time, we talked about 3D geometry. In this video, we're going to find the area of some complex shapes. Starting off with this problem. Two squares shown share the same center and have sides of length 1. The length of AB is 43 over 99. And we're basically asked to find the area of this octagon. So this thingy here in the center, we just have to find the area of it. So how should we do this? Well, intuitively it might seem obvious. We want to find the area of the square, which is, of course, 1, and just subtract off 4 triangles. Okay, so we're also given AB is 43 by 99. And it turns out, by symmetry, because we're rotating it, it's going to be the same everywhere. So what do I mean by that? CD is also going to have a length of 43 over 99. And same for EF and GH. Because of fourfold symmetry, we're rotating the whole square, not just 1 or 2 points of it, right? So 43 over 99. 43 over 99. Okay, so now there's actually one more cool fact about this diagram, and that is the fact that this triangle is congruent to this triangle. So why is this true? Well, first of all, we can easily see that they're similar because angle, 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 angle. So they're similar triangles. But why are they congruent? Well, we know they're similar, and there's this cool argument here that we can use. They both share the same area of the octagon on the inside, and there's 4 triangles on the outside of this octagon. And there's 4 triangles outside the other octagon here. But the thing is, both squares have an area of 1. So that means the sum of these areas must be equal to the sum of these areas. And just like how we found that all those yellow lengths are equal, we also know that all of these lengths are going to be equal by the same symmetry argument. And in addition, we know the area of these 4 triangles is the same as the area of these 4 triangles. And by that logic, we can just say that the area of this triangle is the same as the area of this triangle. And what does that mean? That means the product of this length and this length equals the product of this length and this length by our area of a triangle formula. But wait, our triangles are similar. So this side is scaled up from this side, and this side is scaled up from this side. So if the product of these 2 sides is equal to the product of these 2 sides, but these sides are just scaled up versions of these sides, then these triangles must have the same side lengths. And this whole argument about what I did about proving this is not really necessary in context. You could just notice that, oh yeah, they're similar. They look pretty similar in the diagram, so they're probably going to be similar as well. But just for the sake of completeness, I showed you why these triangles are indeed congruent. And also keep in mind this area argument, as I've seen this in other AMC problems before, where you see the inner area is the same, and because of two figures have the same area, and because of the inner areas being common, the external regions must equal to each other. That's a very standard argument, so make sure you learn that. Okay, now let's continue. So we know all of these triangles basically are congruent. So now let's just assign some variables to all of these side lengths. Let's say x and y, y and x and y, y and x. And we can do this because, all the triangles are congruent. So y is the longer leg of the right triangle, where x is the shorter leg of the right triangle. So first of all, if we got a right triangle here, Pythagorean theorem. X squared plus y squared is 43 over 99 squared. Just Pythag. And remember, we already know the area of the square, 1. So to find the area of the octagon, we just got to find these triangle areas. And how many triangles are there? So the area of the octagon, the area of this square bracket symbol just means area. It's just 1, the area of the square, minus 4 times the area of one of these triangles. And one of these triangles has area half xy. So 4 times half xy, which is just 1 minus 2xy. That's the area of the octagon. So if we can find xy, we're done, basically. And we have x squared plus y squared. Now, if you remember from the algebra chapter, this might be familiar to you. When we have x squared plus y squared and xy, there's this cool factorization that we can use. And that's the binomial square expansion of x plus y. We know that x plus y squared is x squared plus 2xy plus y squared. It's a really good factorization to keep in mind. And what this does is it allows us to use the value of x squared and y squared to find the value of 2xy if we know the value of x plus y. Well, what is the value of x plus y? Take a look at our diagram here. Is there anything, really the only lengths we're given? 43 over 99 and 1. Can we use this to somehow find x plus y? Let me draw it again. 43 over 99, 1. And there's an x here, and there's a y here. Aha! Y plus x. Let's write that. X plus y, which is this segment plus this segment. That's just 1 minus 43 over 99. So x plus y is 1 minus 43 over 99, or 56 over 99. And now let's plug it in to the top equation. 56 over 99 squared. That's x plus y squared. And if we subtract x squared plus y squared, which is 43 over 99 squared, that's going to give us 2xy. And now this is just going to be a little bit of computation. And we can actually use our handy difference of squares formula. So we're not going to directly solve for xy because we want to find 2xy. So that's just one extra computational step. So let's just find 2xy. And to do this, we just have to find this. And we can use difference of squares because we have 99 squared in the denominator. And we have 56 squared minus 43 squared in the numerator. So that's 13 times 99 over 99 squared. Wow, the 99s cancel. That's so cool, isn't it? That gives 13 over 99 as the value of 2xy. So now from here, all we have to do is plug it into our equation above. And now from there, we can just solve for the value of the area of the octagon. So 1 minus 13 over 99 is 86 by 99. And we're asked to find m plus m. So that gives an answer of 185. A cool problem. The main takeaways were the binomial identity. That's a really thing to know. And that allows you, basically it's like a wheel. Imagine you have a wheel. You have x plus y, xy, and x squared plus y squared. If you know any two of these, you can always solve for the third. So if you're trying to find xy, for example, and you know x squared plus y squared, and if you can find x plus y, you can always find the third thing on the wheel. And this is super common in these types of problems. And we also noticed the congruent triangles by symmetry, as well as the need area argument that allowed us to prove that this triangle was congruent to this triangle. But again, in the contest, you could skip this and just assume they're congruent. And then finally, at the end, we just solved for xy, the area of this triangle, times 2, and we just subtracted 1 from that to get the area of the octagon. Let's now move on to our next problem from the AMC 10. Circles are centered at A and B, and they both have a radius of 2. Point O is the midpoint of AB, and OA is 2 root 2. So OA is 2 root 2. OC and OD are tangent to the circles. We know what tangents mean, right angles over here. Draw the center of the circle, we always form right angles. Right angle, another right angle. Because tangents form right angles. Okay, what else do we have? We have circles centered at A and B respectively. EF is a common tangent. Again, tangents, right angles. So let's go ahead and draw our right angles in there. Whenever you see a tangent, just draw a right angle. That should be the first thing that comes to your mind. Draw these right angles. Okay. And we're asked to find this shaded region. It's this curvy, weird curvy region. Interesting. So how should we find this curvy region? Generally, in these types of problems, there's two things you can do. You can either break it up into smaller regions, or you can find a bigger region and subtract some parts from it. In this case, what do we want to do? Well, it's going to be better to find the area of this entire region and then subtract off the areas of these parts. Because there's no easy way to break it up. I mean, we can break it up into these two parts, but what is this really going to give us? Like, what is this top region really? So, but finding these regions, that's a much more doable task because it's just a triangle and a sector. That's so much more doable. So let's do that. First of all, we've got a rectangle here. Let's find the area of this rectangle. 2, radius 2, and they both have radius 2, so this is going to be completely symmetric. O is the midpoint, so of course, if O is the midpoint, then this is also 2 root 2. And then this is also 2. That's a radii. And this is also 2. Now, if you're a good observer and you've had enough practice with, and you've watched the special triangles video, you'll probably notice something a little bit peculiar about this right here. 2 root 2 right angle. That's going to be 45, 45, 90 triangle. And that means DO is 2. DO is also 2 by the exact same logic. So, first of all, the area of the rectangle is just 4 root 2 times 2, which is 8 root 2. And now what is the area of these regions? That's not too difficult. The area of this triangle is half times 2 times 2. 2. And the area of this triangle is also 2 as well. What is the area of this sector? So if we know the radius. All we have to do is find this angle of the sector and we're good. What is that angle? 45, 45, 90 coming in again to save the day. That's 45, and that's also going to be 45. The area of that sector is just 1/8 times 2 squared pi. That's the area of one of the sectors. So pi over 2. The area of a triangle is 2, and sectors pi over 2. So now to find the area of the shaded region, we just subtract 8 root 2 minus 2 times 2 because 2 of the triangles we're subtracting, and 2 times pi over 2 because 2 of the sectors we're subtracting. And that just gives us 8 root 2 minus 4 minus pi, which is the answer for this problem. The key ideas here, 2 strategies when you're trying to find the area of these funky looking shapes. You either break it up into pieces or find a bigger region and take away pieces. In this case, breaking it up not a very easy task to do. Wait, what is this? But if we subtract, we've got nice textures to deal with. So you always want to be considering both of these options, seeing which one's better, which one's easier. Okay, now we're going to take a look at this problem from the AMC. In an equiangular octagon, be very careful here. Equiangular does not mean regular. It just means all the angles are equal. In this case, octagon, equiangular means every angle will be 135 degrees. Okay, so CA is square root of 2, RO is square root of 2, IL is square root of 2, and EN is square root of 2. AR, OL, NI, and EC are all 1. Okay, now this is where the problem starts to get a little bit funky. The self-intersecting, what does that even mean? Cornelia, so C, O, R, N, E, L, I, A, and then back to C again. That's Cornelia, and we're just basically asked to find this total region that's bounded by this self-intersecting octagon. A very interesting terminology they used here. So basically, this is just another example of classic complex shapes tricks. You either break it up or you find something bigger and subtract. In this case, I mean, it seems pretty obvious you want to break it up. There's 2 triangles, or 6 total triangles, 2 of this type of triangle, and 4 of these bigger triangles. So this problem has one really cool trick, and you should basically be using it whenever you see this word equiangular. And that is to extend the sides. Extend the sides of the equiangular octagon. So what we're going to do here is, let me make this a tiny bit smaller. Okay. Let me use dotted lines for this. Extend that there. I'm going to extend that there. So basically, we want to find the area of all these triangles. And to do that, we need 2 things, right? The base and the height. Trying to use Heron's formula here would be an absolute nightmare. We don't really know anything about the side length. So when in doubt of which area formula you want to use, just go with Heron, or just go with half times base times height and try to find the base and the height. I mean, you want to use half AB sine C if you have the angle, of course, and Heron's if you have the side lengths. But if you don't really have any of those things, always want to stick to the default version, try to find the base and the height. Okay, so now we extended this. I know it's a little bit off this diagram, but that's okay. And the thing is because it's equiangular, every angle is 135 degrees. And what does that mean when we extend this? This thing is going to be 45. This thing will be 45, and that makes this 90. Same thing over here. 45, 45, 90 triangles. 45, 45, and 90. 45, 45, and 90. So now we just use our 45, 45, 90 ratios. 1, 1, 1, 1. And maybe I should move square root of 2 a bit lower. But you know what square root of 2 is referring to. 1, 1. By 45, 45, 90 stuff. Cool. And this is also a very standard trick. Like there's another problem, I believe, where you have an equiangular hexagon. And what happens is when you extend the sides of that equiangular hexagon, you get a big equilateral triangle and many small ones in the corner. I made a video about this on my channel earlier, this AMC problem. You can check it out if you want, but it's a great problem, and this is a really great technique. By extending it up, this allows us to basically get a square. 3, 3, 3, 3, and a bunch of right angles. That's a square. And how does this help, really? Well, 45 here. So first thing you have to notice is this is symmetric, of course. Fourfold symmetry. These sides are all equal. The ones are all equal. This is completely symmetric in all 4 directions. So whatever goes on here will happen here as well, right? The next thing to notice is that this angle is in fact 90. Both of these angles are 90. I'll try and hopefully it looks like that in the diagram. But it may not look like that, but both of those angles are 90. And why is that the case? Well, this angle is 135. This angle is 135. So by the sum of angles in a quadrilateral, these two angles must sum to 90. But there's symmetry. It's symmetric. Oh. This quadrilateral is symmetric. So these two angles must be equal. They're both 45 degrees. And that means these two angles are 90. So that means, it may not seem like it, but this is a rectangle over here. And if that's a rectangle, then this height, the height will also be 1. Why? Because if you have a rectangle and you draw here, it's going to be equal to the width of the rectangle. So that height of that triangle is 1. That's cool. The same thing is going to be true on this side, but we'll worry about that later. Because it's literally just, what we're going to do is we're going to find the area of this triangle, multiply it by 4. 1, 2, 3, 4. Find the area of this triangle and multiply it by 2, and then add. So we're not going to really worry about the other side for now. Okay, so we found the height of this triangle. Next, what's the height of this triangle? Well, just like earlier, this is going to be 90, and this is going to be 90, just by symmetry. And that means this is 90, this is 90, this is 90, and this is 90. And now that means CELO is a rectangle as well. That's a rectangle at the center. And that means this total perpendicular distance is also going to be 1. Because the same thing, rectangle. And that means each of these distances is each going to be half. Each of those perpendicular distances. Drop the altitude there. Drop the altitude there. They're each going to be half. And that means the height of this triangle is half. The height of the big triangle is 1, small triangle half. The next question is, how do we find their bases? So something you might notice is that because of the perpendicular lines, these two lines, because it's a rectangle, because this thing is a rectangle, these two lines are parallel. Parallel lines, similar triangles. This triangle and this triangle are similar. Okay, the height of this is half, and this height over here is 1. This part is half, and this part is 1. So the ratio of this height, which is half, to this total distance, which is 3 halves, is 1 to 3. So the bases will also have a ratio of 1 to 3. And that makes this base 1/3 of this tiny triangle. Cool. But then this total distance is 3 here. So each of these two triangles will have a base that's 3 minus 1/3 divided by 2. Why divided by 2? Because these two triangles are congruent, so their bases are going to have the same length, which is going to make 4/3 for each of these two bases. So now we can just add, now we're basically done. We just have to add up the area. We have 4 big triangles. And we have 2 small triangles. The 4 big triangles each have an area that's half times 4/3 times 1, which is 2/3. The small triangle has an area of 1/3 times 1/2 base times height, half base times height, which is 1/12. And now we just add all of this up. So 8/3 plus 2 times 1/12, 1/6, which will give us 17/6, giving us an answer of 23. And that is the answer for this problem. We're done. But next time we're going to talk about the length of complex shapes and we're going to explore some length problems. Be sure to check out the next video. See you there. You can click on it right there.